Hello everyone, I am Tanushree. In this video, we are going to discuss about register allocation. Introduction to register allocation. Register allocation is a fundamental concept in computer architecture and compiler design. It involves effectively assigning variables to the limited number of processor registers, optimizing program performance and reducing memory access overhead. This process is crucial for generating high performance executable code from source code. Role of register in computer architecture. Registers plays a crucial role in computer architecture, serving as the central nervous system that powers the processor operations. This high-speed storage location provides the processor with immediate access to the data and instruction it needs to execute program efficiently. By storing frequently used values, register help to minimize the time-consuming process of fetching information from main memory, dramatically improving the overall performance of the computer system. The number and types of register available in a processor architecture directly influence the complexity and capabilities of the computer. General purpose registers can store a wide range of data, while specialized registers handles specific tasks such as storing the program counter or managing memory addresses. The effective management of these registers is a key focus of register allocation, a crucial compiler optimization that ensures efficient utilization of this limited resource. Principles of register allocation. Efficient resource utilization. The primary goal of register allocation is to efficiently utilize the limited number of physical registers available in a computer's architecture. This involves carefully managing the assignments of variables and temporaries to registers to minimize the need for costly memory accesses. Algorithmic complexity. Register allocation is a complex problem that involves finding the optimal assignments of variables to registers. This problem is known as to be NP complete, making it computationally challenging to solve, especially for large and complex problems. Trade offs and decisions. Effective register allocation requires making strategies decisions that balance factors such as performance, code size, and compilation time. Compiler must carefully weigh these considerations to generate the most efficient code possible. Graph coloring approach to register allocation. Building the interface graph. The first step in the graph coloring approach is to construct an interface graph. This graph represents the live range and variables and their interface, indicating which variables cannot be assigned to the same registers. Next is coloring the graph. With the interface graph in place, the next step is to color the graph using a few colors as possible. Each color represents a unique registers and their goal is to assign variables to registers while representing the interface constraints. The last step is handling spills. If the number of variable exceeds the available registers, some variables will need to spelled to memory. The graph coloring algorithm identifies these spills candidates and inserts the necessary load and store operations to handle the spills. Linear scan register allocation. Liveliness analysis determine which variable can live at each point in the program. Ordering variables. Sort variable by their lifetime or number of uses. Allocating registers. Assigning variables to registers in order spilling when necessary. Linear scan register allocation is a simple yet effective approach to assigning program variables to the limited set of physical registers available on a computer. It works by first analyzing variable liveliness to understand which variable need to be kept in register at each point in a program. It then order the variable based on their lifetime or frequency of use and greatly assigns them to available registers, splicing variable to memory when necessary. Splicing and reloading strategies. The first is registered splicing. When the number of live variables exceeds the available number of registers, the compiler must spill some variable to memory. This involves selecting the appropriate variable to spill based on factors like frequency of use and lifetime. The next is reload optimization. Reloading spilled variables back into register is a crucial step. Compilers employ techniques like coalescing and load hosting to minimize the number of reload and improve performance. Next is stack frame management. Efficient allocation of stack frame is crucial as it affects both spacing and reloading. Compiler must carefully manage the stack layout to reduce memory access and optimize register usage. And last is profile guide optimization. Advanced compilers can leverage runtime profiles to guide spacing and reloading decisions, further improving registers allocation by targeting the most critical code paths. Interface graph and liveness analysis. Interface graphs are a key concept in register allocation, representing the conflicts between variables that need to be stored in register. These graphs depict the when variables live range overlap, indicating that they cannot be assigned to the same register. Liveness analysis is a process of determining a variable's live range, the period between when it is defined and when it is last used. This information is crucial for constructing the interface graph and making optimal register assignments. By carefully analyzing the interface relationship and live range of program, variable register allocation algorithms can minimize spacing and ensure efficient use of the available registers. Register allocation algorithms. Graph coloring approach. One of the most widely used register allocation algorithm is the graph coloring approach. It models the interface between program variables as a graph, where each node represents a variable and each edge between two nodes indicates that the variable cannot be assigned to the same register. Linear scan algorithm. The linear scan algorithm is a simpler and faster alternative to graph coloring. It makes a single pass over the code, assigning registers to the variable based on their live range, which represents the intervals in which a variable is active. Chaitin's Bridge algorithm. This algorithm is an advanced graph coloring approach that incorporates live range and splitting and splicing. It recursively selects variable to spill and then color the remaining variables, ensuring that the number of registers used does not exceed the available hardware registers. Optimization and trade-offs in register allocation. Register allocation involves carefully balancing of various optimization and trade-offs. One key consideration is minimizing the number of registered spills when where values need to be temporarily stored in memory. This improves performance but may increase code size. Another trade-off is between register pressure and instruction count. Using more register can reduce the number of load and stores but also increase register pressure. Compiler may also employ hesitate to prioritize certain variables or expression, allocating more registers to hard code path. This can boost performance but risk in introducing bias and suboptimal allocation in other areas. Leveraging profile data can help inform these decisions but come with additional complexity and runtime overhead. Ultimately, register allocation in an iterative process of making informed choice and compromises to achieve the best overall performance. Advancement in compiler technology and hardware architecture continue to expand the optimization possibilities while also introducing new trade-offs for engineers to navigate. Practical considerations and real-world implementation. Register allocation is a crucial component of any optimizing compiler, and its real-world implementation must consider a varieties of practical factors. This includes the specific hardware architecture, the characteristics of the target application, and the trade-offs between code size, execution speed, and the compile time performance. Compiler must often balance the need for efficient register usage with the realistic of limited register resource. This may involve sophisticated technologies like splicing and reloading, as well as carefully analyzing of variables liveness and interference. Implementation must also handle edge case such as calling conventions, function parameters, and calling context. Behind the technology challenges, real world register allocation must also consider the practical need of software development and the end user. This may also include debugging, profiling, and runtime optimization, as well as the compatibility and third party liberties. Achieving the right balance of performance usability is a key goal for any production ready register allocation system. Thank you for watching my video.